Welcome to week 5. So we're 5 weeks into the flipped classroom, and I hope it's going well for everybody. What I've decided to do with this week is to provide an overview of the readings based upon some of the feedback that I've received so far, and I think that would probably be a good idea. So first, this week's reading was Cohen and Cohen, West and Aiken, chapters 6 and 7, and I just want to highlight some of the points, and a lot of these points will be, well, I'll provide further elaboration on the points in the specific videos. But overall, chapters 6 and 7 have to do with some of the finer points in linear models. So in chapter 6, there were essentially 6 pieces that I think are important for people to understand. And that is the idea that first, linearity does not mean necessarily that the relationship that we're trying to estimate is necessarily straight line, a straight line or rectilinear, but that linearity means that there is an additive function. So when we say the general linear model, general means that the model generalizes to both continuous variables as well as to categorical variables or nominal level variables, which we're going to get to shortly. But that the L part, the linear, means that each of the components that we include in our models are linear, that they're linearly additive, and that it is a sum of each one of those components. And a good example is that we could have polynomials where here in this line you can see that we have 3 regression coefficients, b1, b2, and b3, but they all deal with x. And here's x1, and I should put 1 here, and this is x1, and then x1 squared, and then x1 cubed. And the reason why this polynomial model works is because what we're expecting is that there is an additive function that allows x to have a polynomial or a complex relationship with y, so that x can have a linear component, that's this part, a quadratic component, and a cubic component. And then unfortunately these are not orthogonal, but there are ways in which we can increase our power by creating orthogonal polynomials of our parameter or of our predictors, because of course x1 is confounded with x1 squared and x1 cubed, and so there are ways in which we can make these independent. And then what happens if we have data that do not look rectilinear, but we have an assumption that they are rectilinear, particularly right here in this term? Well, there are ways in which we can transform our data to fit our model. So in other words, we start out with data that don't comply with the general linear model, and we convert those values into values that fit. And that's what transformations are about. And there are various ways in which we can do this empirically, or we can do it theoretically. But now there are also alternatives to the general linear model, and that we can have non-additive models, that is, that they're non-linear regressions. Now that's different than saying that the polynomial is a non-linear model. It is a linear model because it is inherently additive. So a non-linear regression typically has something like multiple parameters with multiple variables. So it might be x1 raised to the x2 power, and there are b's for both x1 and and then a b for x2, so that there is some form of a power relationship between 2 of our predictors when predicting our y. And that would be a nonlinear regression model. And then there are other non-parametric, so nonlinear regressions, I would assume that there would be b's that are estimated. But there are other non-parametric regression models like LOS and other things like that are completely data-driven, And Cohen, I think, dispense with that right away and just say that these are oftentimes they are atheoretical and probably not terribly generalizable. So chapter 6 is a good introduction to what that L means in the GLM. Chapter 7, though, moves us in the direction of where we need to be this week. But don't ignore chapter 6. Chapter 6 is really an essential piece for understanding where an interaction fits with the additive model. And that's precisely where Cohen, West, and Aiken start with, is they talk about interactions and additive effects, and that interactions really are additive effects, that they are added to what we would consider to be our main effects or our primary predictors, but that interactions are tested above and beyond those main effects. And so they are additive, but they are multiplicative. So they do in some ways violate what we would think of in terms of rectilinear relationships, because if you think of interactions and main effects, like up here in these summative models, this plus sign is an OR, is a logical OR. So what I'm saying is x1 or x1 squared or x1 cubed. And that's a little bit different than if I had a model with y equals, b1 x1 plus b2 x2 plus b3 x1 times x2. Because what this is saying is these pluses are ORs, are logical ORs, but this multiplicative sign here is a logical AND. And so therefore interactions are testing, when we're testing in the general linear model, we're testing OR statements. So it's x1 or x2 or x1 and x2. And that's what we're testing in these interactions, or in a term that most of you are familiar with now, that interactions are called moderated effects. And one way to understand moderated effects is, first, in order to appreciate or interpret B3, oftentimes it's best to center our variables. By centering them, what we're doing is we can eliminate some non-essential multicollinearity, but more importantly, we eliminate some of the metrics that really interfere with a smooth and easy transition from us interpreting main effects to interpreting interaction effects. And centering has all sorts of ways of doing it, but the best way to center, and you'll see this later, is that when we center our variables based upon mean centering, but we don't standardize them because we want to include the relative differences or in variability between our predictors and our dependent variable. So centering is something that will be novel for most of you. What will not be novel for most of you who have taken classes with me before, particularly 611 and 612, I go over simple slopes and simple intercepts, and Cohen, West, and Aiken do a nice job of elaborating these simple slopes and simple intercepts, how you calculate them, what the logic is behind them. And then the last bit of this is really just a matter of the details. Once you figure this out, once you figure out how to do simple slopes and simple intercepts, that it is fairly straightforward in interpretation, but here are complications. Not having a priori hypotheses leads to a lot of post hoc theorizing. We got to be careful about that. There are also many patterns that we may observe in interactions, and Cohen, West, and Aiken give you lots of those, and I've gone through those in previous classes, but it's important for you to appreciate and to expect what those interaction patterns are, lest you be tied to just the data and having to do post hoc theorizing why that interaction exists. Certainly there are more complicated models, particularly when we get into multiple predictors, like many predictors, 5, 10, 15, 20, something like that, where you get really complicated and complex models that involve many interactions. And also when we have predictors that can't necessarily be dichotomized when we're trying to plot things, because here plotting is an important aspect in understanding what we're observing. And if you can plot your interactions, sometimes it's a good way to just gain a gist of what's happening with your data. What happens when you have predictors that have many different levels, like maybe 5 or 10 or 15 different levels? Well, for each level you get a different curve, and sometimes it's very difficult to figure out where the interaction is, and that would just be from a two-way interaction. But it gets more complicated when you have a three-way interaction and a four-way or n-way interactions. Complicating even further is what happens when you have curvilinearity, like you have a curvilinear relationship, and that you have interactions where the curve parameters change. Well, now we get into really difficult interpretations, and this is where in social science we haven't done a great job with this, because mostly in social science we rely heavily on tables. Figures oftentimes exclude the raw data. So what we're going to talk about is how these curvilinear relationships, particularly with moderated effects, oftentimes are very sensitive to just a few data points. And we'll go over diagnostics and how to identify when certain observations influence the parameters, particularly the interaction parameters, such that they're probably not going to be terribly stable, nor will they generalize. And all of this we're going to wrap into power considerations when testing any type of interaction, and that power is oftentimes threatened by testing lots of interaction effects, but particularly the moderated or interaction effects themselves tend to be underpowered. And the reason for it is that in almost all partitioning of variance, the interactions have a lower standing, and that is main effects get partialed out first before the interactions, and when that happens, the interactions have less variance in Y to be accounted for. So chapters 6 and 7 lay the foundation for moderated multiple regression, which is going to be our first topic after Module 1, and it's going to set you up for Module 2 for appreciating more complicated models. So stay tuned for the rest of the videos for week 5.